In this chapter, we will study what we mean by lateral stability, spoke dimensions, spoke elastic modulus, spoke tensile strength, and then a qualitative discussion of the lateral flexing of wheels. A quantitative discussion will follow.
There's math here, I fully admit, and algebra used quite a bit. Add vectors and trig, a challenge not big, but no calculus, don't throw a fit. In the film clip coming next, you'll see a powerful rider coming toward you. Look at how he rocks the bike back and forth as he puts power to the pedals.
Jay is rocking the bike back and forth to put into it power in excess of 1,000 watts. And as he does, he's putting a side load on the wheels in one direction and then the other. How much the rim flexes back and forth from side to side is what we mean by lateral stability. So in this chapter and the next, we're going to build up some wheels and put them through a series of tests where we vary one component at a time. These are the three Supreme spokes we're going to be studying closely. The one on the left, the leader, is a straight gauge spoke. The race and the laser are both double-butted in the dimensions shown. Below is the mass in grams for 64 spokes of 260 millimeters for each of those spokes, 431 grams for the leader, 363 grams for the race, and 273 grams for the laser. And you can see also, if you look below that, is the strength of the middle section in terms of newtons per square millimeter. Here are some quotes from some emails I have from the Chief of Quality Control at Supreme, and he tests everything over and over and over again. So I take it to the bank here that the leader spoke has a modulus of elasticity of 200 gigapascals, the race 230, and the laser 260. The leader is 200 gigapascals over its length. The race is 200 at the very short ends, but 230 in the long midsection. The laser also 200 at its short ends and 260 in the long midsection. So I've added that information to the technical specs for each spoke. Since we're given the strength of the middle sections on these spokes and we can calculate the cross-sectional area, we should be able to compute the total tensile strength of each spoke. For the leader spoke on the left, since a range is given of strength on the middle section, we'll just pick a number in the middle of that as the average. If I look at the leader spoke and I multiply the number of newtons per square millimeter times the cross-sectional area, I get the total number of newtons of strength in the spoke. Likewise, for the race spoke, 1,300 newtons per millimeter squared times its cross-sectional area gives me 3,303. And for the laser, 1,500 newtons per square millimeter times 1.77 gives me 2,655 newtons. Now, just a comment here, even though the total strength of these spokes declines going from left to right, even that laser spoke with 2,655 newtons is very, very strong, and that is a far larger amount of tension than you would ever put on any wheel. As we go from left to right, from the leader spoke to the race spoke to the laser spoke, the diameters go down from 2 to 1.8 to 1.5. But also going from left to right, the strength of the middle section of the spoke increases from 1100 to 30 newtons per square millimeter to 1300, and then 1500. So if we just compare the cross-sectional area and tensile strength of the leader spoke on the left with the laser spoke on the right, we see that the laser's cross-sectional area goes down by 44%, but the tensile strength only decreases by 25%. And I think that's kind of an interesting observation. Here's a graphic of a generic wheel, and I'm going to build 3 wheels, 3 24-spoke wheels, and I'm going to use velocity race hubs, velocity deep V rims, Supreme spokes, and Supreme nipples. The only variable will be the Supreme spokes I use. In the first case, we will use the leader spoke with a modulus of elasticity as shown. In the second wheel, it'll be a race spoke, and in the third wheel, laser spokes. This is a nice photo of a velocity race hub, but the camera angle doesn't let me use it very well in a drawing, so I created this graphic. And I was pretty careful to scale everything correctly. Here we see our wheel built up with the velocity race hub compared to the wheel with the generic hub, and this is a good opportunity to point out something that's interesting. This is my overlock nut width of 130 millimeters, and my velocity hub has the same overlock nut width. On the left, these are where my left and right flanges are, where the spokes attach, and on the velocity hub, they are here. Now, these are the free hub bodies. The wheel on the left has a 10-speed free hub body. The wheel on the right has an 11-speed free hub body. The 11-speed free hub body is longer, and that necessitates moving the drive side flange closer to the center of the hub for the 11-speed than is the case of the 10-speed. That means that angle theta for the wheel on the right is going to be smaller than angle theta for the wheel on the left. These are my tension vectors. These are the vertical components, and clearly my horizontal component for the wheel on the right is smaller and shorter than the horizontal component for the wheel on the left, and that will mean that the wheel on the right has less side-to-side stability. My spoke length calculator gives me 259.06 millimeters on the drive side and 271.01 on the non-drive side. And that gives me the angles that you see here, which are quite typical for a rear wheel. Then I put my wheel onto my experimental table. The graphic here implies that the rim is only supported at 2 places, but when you see my apparatus for testing, you'll see that the rim is fully supported all the way around. Then we're going to observe our center line and attach a weight down through the hub, which will pull the hub down in relationship to the rim. When the hub is pulled downward, what stops it from continuing to move downward is that the tension on the drive side spokes increases. When that happens, the vertical component of the drive side tension increases also. Even though it's going to be a little blurry, I'm going to expand this section because those arrows are so tiny. And when I do, we see that these original tension vectors and these original vertical components increase to these tension vectors and these slightly larger vertical components. A static equilibrium is reached when the downward force from the weight is equal to the sum of the additional vertical components of all of the drive side vectors. How far down the hub moves to reach a new static equilibrium depends on the elastic modulus of the spokes and their dimensions.
Being good scientists, we'll do some calculations and then form a hypothesis. And then later on in the video, in the empirical portion, we'll take some measurements and test the hypothesis and see if it's correct.
We're going to expand this so we can see it better. Let's build this up slowly because a good mental picture of what's going on is going to be key to understanding this. Here is the rim supported on either end. There's the hub. That line bisects the hub, and it's a 130 millimeter hub. Therefore, the distance between each lock nut and the center line is 65 millimeters. For testing purposes, my wheel is built with radial spokes on both sides. These are the dimensions we worked out just a minute ago. We're going to put on the drive side spokes 1,300 newtons of tension. Now, obviously, there will be tension on the spokes on the non-drive side as well. We have no control over what the magnitude of that is. That's a function of the geometry of the wheel. When the wheel is dished and I have 1,300 newtons on the drive side, the non-drive side is what it is. Let me add an editorial comment on the way I'm showing my vectors that some of you may object to unless you understand why. I can show the tension on my drive side vectors in two equivalent ways. I can show them like this, or I can show the vectors like this. In other words, I can show my vector as the spokes pulling the rim toward the hub, or the hub toward the rim. If I resolve those tension vectors into horizontal and vertical components, I get this depiction here, which is correct. If I show my tension vectors like this, then my horizontal and vertical components look like this, and that is also correct. My problem is I want to show those tension vectors like that because I think it's intuitively clear to show them that way. The problem is that that makes my vertical component point down. But I need to have those vectors pointing up so that as I add weight to the hub and the hub is pulled down, the opposing force as those vertical components increase in length is seen as opposing the downward pull of the weight. So with that explanation, I'm hoping you'll give me license to show those vertical components pointing upward. Another way of depicting the wheel is to show it as a free body diagram, and some of you may appreciate this way of looking at it, but I don't think that the free body diagram is as easy to understand. So while it may be a little bit more technically accurate to some people, I'm going to continue to use the same method I've been using all along. I know that my angle here is 3.76 degrees, and therefore the magnitude of the vertical component of the tension vector on the spokes, which is that little arrow right there, is going to be equal to the total tension times the sine of 3.76 degrees, which is 1,300 newtons times 0.0656, and that works out to 85.3 newtons. Now, that's a small number compared to the total tension. It's always going to be small because of the geometry of the wheel. It is that 85.3 newtons on each drive side spoke, the vertical component of it, and the corresponding equal amount on the non-drive side that provides lateral stability to the wheel. Now, we haven't got much room, but let's label those like that. And that, of course, is representative of the vertical component on every one of the spokes on the drive side. So if this is a 24-spoke wheel, I have 12 spokes with that amount of tension on the vertical component of the drive side vector. Some people are going to be unhappy if I don't finish out this diagram, so let's put those vectors in on the non-drive side. I have to get the same value, which is 85.3 newtons. That comes from a smaller magnitude on the non-drive side vector. However, the angle is better, so I end up with the same amount of vertical force. 699 newtons on the non-drive side vectors. My wheel here is strong and stable, and everything is in perfect equilibrium. But we won't let it stay like that. We're going to put a side load on the hub and then pick this discussion up in the next chapter.